Good morning. Welcome to the first session of the third day of Eurocrypt. Today the session is about proof system. I'm Rosario Gennaro. I'm going to be your host for the morning. We're going to have three very exciting talks. If you saw the invited talk by Lieb and Sassoni yesterday, you'll see a lot of that stuff today. The first talk is Inefficient Prover Zaps from Hard-to-Invert Functions by Marshall Ball and Dana Dachman-Soled. And Marshall will be giving the talk.
Thanks, Rosario. Thank you all for coming to the first session in the morning, especially after the rump session last night. Let me just check. I guess I can't gesture with this thing. Okay. This is work with Dana Dachman-Soled. So I was trying to think about, I wanted to give this talk to be light, given this first thing in the morning, but I couldn't figure out how to give it without introducing at least 7 different definitions, which is something you're never supposed to do. So I decided to try to sort of break things down a little bit before I get into the weeds, so you can stop paying attention if you want. So the quick takeaway of this talk is that one-way functions are not necessary for a non-trivial notion of zero-knowledge proofs for NP. Of course, it's not going to be actual zero-knowledge proofs, but something else. And in slightly more detail, what you will see in this talk is a new primitive that we introduced that's below one-way functions. We call hard-to-invert functions. And we show that using this primitive, you can build something called zaps, which are two-message witness indistinguishable proofs for NP, where the prover runs in sub-exponential time. And then at the end, if we have time, we'll show sort of an application of this main theorem to constructing hardness, giving hardness in NP intersect co-NP in the non-uniform setting. Okay. All right, so probably what you're wondering is what is a hard-to-invert function? So the starting point is a one-way function, which hopefully all of you are familiar with. So one-way function is a function f that's easy to compute in one direction and hard to invert given a random image. So what is a hard-to-invert function? Well, it's a generalization of a one-way function where we just remove the requirement that it's easy to compute in the forward direction. So it still needs to be a function, but no longer do you need to be able to compute it in polynomial time. What you do need to be able to do is to prove that given a xy pair, that indeed x evaluates to y. You don't need to necessarily be able to verify this in deterministic polynomial time. It's fine if you can verify it with a witness or a proof. And it's easy to see that, hopefully, that one-way function is necessarily a hard-to-invert function. But it's not too difficult to see, I guess, that, I'm not going into it here, but there's a separation between these two notions. So hard-to-invert functions do not imply one-way functions, as far as we know. In particular, you can build them from average case hardness and TFUP, but anyways. Okay, so that's a hard-to-invert function. So what is, I need to start talking about zero knowledge. So hopefully all of you are familiar with zero knowledge proofs. So it's we have an interactive proof between a prover and a verifier with the various properties. Completeness, that you should always accept true statements. Soundness, the verifier should always reject false statements. And zero knowledge, the verifier should only learn that the statement is true. And this is formalized, as all of you are hopefully familiar, with the notion of a simulator. You can simulate the prover and verifier's interaction, the verifier's view. Okay, what do we know about zero-knowledge proofs? Well, we know that one-way functions suffice to build zero-knowledge proofs for NP, and a sequence of works has shown that effectively one-way functions are necessary to build zero-knowledge proofs for NP. Okay. In this talk, we're interested in very zero-knowledge proofs with limited interaction. So the most natural notion is a non-interactive zero-knowledge proof. So here the prover and verifier have a common reference string that they share, that they can see in the sky, and the prover is just allowed to send a single message to the verifier instead of interacting. Sorry, the clicker's not working. Okay. So typically, in the case of this talk, we're considering sort of two models for this common reference string. So one we call the common random string or the common reference string, or the CRS model, where this random string is allowed to be structured. And in the other case, we're considering where the random string needs to be truly random, uniformly random. And in the common reference string model, we know that one-way functions suffice to build NISICs for NP. But in the uniform reference string model, we only know how to build NISICs for NP from one-way permutations and not one-way functions. So you need some additional structure, right? There's sort of a big difference here, at least as far as some of us are concerned. So one big open question that was sort of motivating us in getting into this was, do one-way functions imply non-interactive zero-knowledge proofs in the uniform relative to a uniform random string? So recent work of 2 years ago showed that you can build NISICs in the random oracle model, but we wanted something a bit more explicit. In this work, we don't actually resolve this question, so it's still open if you're interested in working on this. And instead, we show that something weaker implies something weaker. So we show that hard-to-invert functions imply these zaps. Okay. So what is a zap? So this is something introduced by Dwork and Knorr. And it's a very simple proof. It's just two messages, a two-message sort of AM-style proof, where the verifier sends a single random message, uniformly random message, and the prover responds. So this kind of interaction pattern is impossible to achieve zero knowledge with. So you can't get regular full zero knowledge, and instead you get something we call witness indistinguishability, which means that the verifier can't distinguish between if the prover has a witness W1 or versus if the prover has a witness W2. Okay? And note that this notion, I claim it's non-trivial, but it is trivial if, for example, your language only has unique witnesses, then this property becomes trivial to achieve. And similarly, if you allow the prover to be arbitrarily inefficient, then again, this also becomes trivial, unlike traditional zero knowledge, because the prover can just find a canonical witness and send that. Okay? So we claim that this becomes non-trivial as far as we know, assuming, say, NP can't be solved in sub-exponential time, if the prover runs in sub-exponential time. Okay, so what do we know about these zaps? So Dwork and Knorr showed that zaps, why am I talking about zaps and non-interactive zero knowledge relative to a random string? Well, Dwork and Knorr showed that these two notions are equivalent if under the restriction that the prover is efficient. And we can build these NISICs with trapdoor permutations to get an efficient prover. All right, and then in a work again with Dana and Mukul Kulkarni in 2020, we sort of looked at this connection in the inefficient prover setting with the goal of building these things from weaker assumptions. And we were able to show that, right, at least one direction still holds. So, right, given a NISIC with a uniform random string, even if the prover is inefficient, you can still get a zap, a non-trivial notion of a zap out of this. And so that allows us to sort of instantiate this thing with a one-way permutation instead of a trapdoor permutation. Okay, and the way that this goes is it goes through this notion of what we call an offline NISIC relative to a uniform random string. Okay, and so in this work, we show how to build this intermediate notion of an offline NISIC, which I'll tell you about in a moment, from hard-to-invert functions. Okay, And yeah. All right. And additionally, right, we show that once you have these zaps which follow from these offline NISICs, that by sort of compiling a sequence of transformations from the literature, you can get hardness in NP intersect co-NP in the non-uniform setting. But don't look at everything there, I guess, yet. It's too much. So instead, let me tell you what is an offline NISIC. It's a NISIC with what we call offline simulation. So typically, right, the simulator is required to be polytime. Here, we have sort of a slightly different notion. So you have a distribution over polynomial. The simulator you can think of as a distribution over polynomial-sized circuits. Okay? But this distribution is not necessarily efficiently samplable. So you sample a circuit, a small circuit from this distribution, and then the circuit is given the statement that you're trying to simulate, and it produces the simulated CRS and the simulated proof, and you shouldn't be able to distinguish. So contrast this with a NISIC, which, like, right, you can shape the definition. You can view this as like the same, except I require that the distribution over the circuits is samplable, efficiently samplable. Okay. So now I'm going to sort of get a bit more into the weeds as to how this goes. How do we build an offline NISIC from a hard-to-invert function? That's sort of our goal. I'm not going into how the zaps follow, because this is from prior work. Okay, so we follow this classic FLS framework. So the FLS framework works as follows. First, you build a NISIC in what's called the hidden bits model, and then you figure out how to instantiate this so-called hidden bits model. Okay, so what is a hidden bits proof? What is a proof in a hidden bits model? You will have a bunch of boxes in the sky. Instead of a CRS, you have a bunch of boxes, and inside each box is a random bit. And the prover can send a proof, and he can also open the boxes. And you should think of these boxes as like perfectly binding commitments to random bits, and the prover has the ability to open these commitments. Okay, so what do we need? How are we going to modify this for an ONISIC, to build this offline NISIC? Well, all we need is sort of what we call relaxed hidden bits. In the first part of this, there's absolutely no change. You just use the same exact proof system. The only difference is we want to instantiate these relaxed hidden bits from these hard-to-invert functions. Okay. And what is the relaxation? It's like a commitment. It's exactly the same. We need the same properties, except we no longer require that sort of the committer in this commitment scheme is actually efficient. Okay, so looking in more detail, what do we need from these hidden bits? So we have a prover, these relaxed hidden bits. We have a prover who runs in exponential time, and we have a verifier who runs in polynomial time. And right, we have this random string R that's sort of our commitment, and the prover wants to prove that this is a commitment to a bit B, and right, with a proof pi. So you can think of the pi as the opening. So right, what we want is with high probability over R, we want what I call, for this purpose of this talk, total perfect binding, which means that basically for almost every R, there's a unique B that the verifier will accept with some proof. Right? You can't open to both 0 and 1. We want binding, and not only that, but we want like virtually everything to be a valid commitment, unlike many commitment schemes that we know. And on the other hand, we want computational hiding. You shouldn't be able to distinguish between commitments to 0 and 1. Okay, and then we also need that the bits are unbiased, but I didn't write that here. So right, what is the non-relaxed version? The non-relaxed version just says that you can efficiently sample these triplets, but we don't require that. Okay. So a starting point of our construction will be how to build this in the style of FLS. So you have a one-way permutation. You have a hardcore predicate for this one-way permutation. So what do? You take R, you invert the one-way permutation to recover X, and then you compute the hardcore predicate of X. Then we send X and B, and the verifier simply checks, does X evaluate to R, and is the hardcore predicate actually indeed B? Right, we have total perfect binding because, right, you can always invert, and the preimage is always unique, and therefore the bit defined by the hardcore predicate is also unique. And we have hiding because, right, this is a hardcore predicate. Okay, so now let's try to use, let's try to do this from a one-way function. I'm going to work with one-way functions instead of these hard-to-invert functions, but if you check, then everything goes through with a hard-to-invert function, but I'm just sort of saving myself from writing more proofs and everything. So let's replace this one-way permutation with a one-way function. So what is the problem? Well, there's two problems. First of all, the image of this function, right, this function might not be onto, so maybe most random strings don't even have preimages at all. And maybe if they do have preimages, then maybe they have multiple preimages, and the hardcore bits are distinct. Okay, so let's try to fix the first problem, the problem of onto-ness, the problem that like not everything even has a preimage. So what is a natural thing to do? A natural thing to do is to just hash the output of this one-way function. Okay, so we'll do this with a t-wise independent hash. Great, that works most of the time. But now things are even less unique than before. Now we have even more preimages. Okay, so what is the next natural thing to do? Well, now we're going to constrain the set of allowable preimages. We're going to introduce another hash function. We're going to say, okay, well, a preimage is only valid if it hashes to 0. Okay, so then sort of with high probability, we'll be able to constrain the number of valid preimages. But unfortunately, at least basically using this technique, we can't sort of force there to be a unique preimage with high probability, which is sort of what we need. Okay, so right, this set of this intersection between this blue and gray, which is what we want, is not going to be a singleton with high probability. It will be, if you try to set the parameters, right, even the number of preimages might change depending on what the R is, and it's a mess. So what do we do instead? We give up on the singleton. Instead, we use all of the preimages at once. So instead of taking a single preimage, you take the set S of all of the preimages, which you can show will be poly-sized with high probability, and we're going to use that. And right, we're going to compute a hardcore predicate, which is evaluated on this set, not just a single preimage, but the set of all preimages that match these constraints. Okay, great, but you should be suspicious, because now how are you going to verify that you actually have the entire set? It's not really clear how to do this. And if you don't have the entire set, the prover can selectively remove something and change the hardcore predicate. So we're no longer binding. Okay, so we're almost done. So we're going to do, instead, how do we fix this? We're going to do this many times, and then take the majority of the hardcore bits. Right, and then we're going to have a check that the size of the sets that the prover sent are distributed correctly. Okay, and so what we use is a protocol from Akavia, Goldreich, Goldwasser, and Moskowitz, used in the context of proving it's hard to build NP-hard one-way functions. That says that if we look at sort of the statistics of the frequencies of various sizes of sets, as long as these two things are close, then most of them have to be exactly right. Right, the domains are poly-sized because we're going to sort of just cut things off at a certain polynomial limit, and so you can check this, and as long as they're close and the right notion of distance, earth mover distance, most of them will be correct, and then the majority is sort of robust to any change. Great, but now there's one last problem. Where is the verifier going to get these statistics about the function? Well, from the prover. So we ask the prover to produce the necessary statistics and the proofs that the statistics are correct, and we use a different proof system from a different context. Okay. So I'm going to skip this as I'm out of time and leave you with some open questions. The second one I already mentioned, but we don't understand sort of the minimal assumptions for any of the things that I introduced today. And yeah, getting better explicit hardness in NP intersect co-NP remains an open question. Thanks.
We have time for one or maybe two questions.
for great work. So we know from the construction from trapdoor permutation to NASIC, actually we require some enhanced properties of the trapdoor permutation, roughly saying the one witness still holds given the seeds to sample the image. So
Sorry?
So we roughly need some enhanced property for the of the trapdoor
yeah.
permutation. So do you require such enhanced property?
No.
So why is there something? How did you bypass this?
Well, like I guess it makes more sense when you're looking at how to build. Like, right, you need to send the proof systems. The proof system with a one-way permutation is like in some sense more naive.
Yeah.
Then right, you're not like sampling a public key yourself.
Okay.
Right. We don't need to. The prover doesn't need to be efficient.
Okay.
I don't. Yeah. I don't. Yeah. Okay. I can talk to you more about it offline.
Okay.
Yeah, I think it's the inefficient prover.
Yeah.
I have one question.
Sure.
So the hard to invert function seems to need a hardness of search and easy decision, right? Because you need to detect that the solution is correct, but you shouldn't be able to find it. Right?
Yeah.
So do you have any candidates? I mean, I was thinking about Diffie-Hellman in
Candidates that don't imply one-way function.
No, you're right.
Yeah.
Oh, that don't imply one-way function, right?
So, yeah. So, right, I sort of briefly mentioned if you have any average case hardness, TFUP, which is
right.
TFNP with unique solutions, then you can get this kind of thing. But this doesn't seem necessary. I think it's a great question. Does this follow from average case hardness in NP, period? I don't know. Yeah.
Thanks. All right, let's thank the speaker again. Our next talk, let me get my program out. Right. All right, our next talk is Reed-Solomon proximity texting with super fast verification by Gal Arnon, Alessandro Chiesa, Giacomo Fenzi, Eilon Yogev, and Giacomo Fenzi will be giving the talk.
Thank you for the introduction. So yes, today I'm here to talk about WHERE. So first of all, let me preface you, we're going to use the random oracle a lot here. So we're going to see that a lot. So let me motivate a bit what our work does and what are we trying to improve and what we're trying to construct. So the object of our investigation is succinct interactive argument of knowledge. So, as is common, you're trying to show, as a prover, knowledge of a witness to the membership of an instance in a relation. So you have a prover, so for example, a preimage. So you have a prover and a verifier. Prover gets instance and witness. Verifier gets the instance. The prover sends a single short message. And then the verifier outputs a bit that says whether it is convinced whether the proof that the prover provided convinced him of the claim statement. And in this talk, I'm going to be focusing on hash-based narcs. So I'm going to allow the prover and verifier to have access to a random oracle. And I would like soundness and knowledge soundness to hold in the pure random oracle model. So without any other kind of computational assumption, like groups or lattices, for example. So in practice, hash-based narcs, they gave a lot of great properties. Because when you take the random oracle and you heuristically instantiate it, the resulting snarks has a lot of desirable properties. So first and foremost, prover and verifier only have to agree on which hash to use. There's nothing else that they need to choose. So you are able to get a transparent setup. The proof system only uses symmetric cryptography, so there is no need of expensive public key crypto. This usually makes the prover much more efficient in practice. Further, you also get plausible post-quantum security. In fact, all the protocols that we'll be talking about today can be proven secure in the quantum random oracle model. So these are a very nice set of things to have. And this has led to a lot of practical adoptions of hash-based narc in practice. And here I just put a bunch of companies' logo on the slide. Not too important for the talk. So, okay, so having established that hash-based snarks are nice, this kicks down the count down the road a little bit more, and we want to figure out how to actually construct hash-based snarks. And there's a very established recipe for doing this, which is the BCS16 construction. So this is going to compile something called an interactive oracle proof. So if you were at Ellie's talk, you might have seen these things beforehand. So this is a very nice information theoretical primitive. So you might have seen PCPs before, probabilistically checkable proof. These are proof systems in which a prover and a verifier interact, and the prover sends like these long oracle messages, which the verifier is not allowed to read in full. This is a PCP. In an IOP, you actually have many rounds of interaction in which the prover can send all of these oracle messages. These are long, the verifier doesn't read them entirely. But at the end of the interaction, you can like choose a few positions in which to actually query things. So once you have this information theoretical object, you can compile it into like a succinct argument in the ROM by using Merkle trees and Fiat-Shamir. So you get exactly the dash-based snarks that I would want to construct. And just for your intuition, you can think that the two main efficiency features of the IOP are proof length and number of queries. And you can think of this proof length to be very large, like linear in the size of the witness, while the number of queries is like logarithmic in the size of the witness. And in the compile argument, you depend linearly in the number of queries, but only logarithmically in the proof length. So concretely, this leads you to like a succinct argument where the argument size ends up being small, in the order of tens of kilobytes. So in this talk, we're going to be focusing on the IOP part of the construction. And let me kick down, and I'm going to do another compiler. So IOPs traditionally are constructed by taking something, a relaxation. So these are polynomial interactive oracle proof. So these are exactly before an IOP, but now the messages that the prover sends are assumed to be polynomial, and the verifier can ask for evaluation at any point that he desires. And okay, so this will, so later on, we want to compile this in an IOP, and the way that we are able to force the prover to follow this blueprint to send polynomials is by using error-correcting codes to make a redundant encoding. So this is what this would look like. So I take my polynomial IOP prover and verifier. Whenever the prover sends you a polynomial, I will instead send a Reed-Solomon encoding of the polynomial. And then when the verifier wants to query the polynomial at a point z, I will let the prover provide me the answer to that query. But now, since we are not in the business of trusting provers, I'm going to have to do something to hold it accountable. And that tool is a very beautiful tool from information theory, which is a Reed-Solomon proximity test, combined with a quotient. And this will be important later on. But for now, for this high-level intuition, you can think that the IOP, and thus the resulting arguments, inherit the asymptotics almost entirely from this proximity test. So by improving the proximity test, you can just improve the entire construction. So let me introduce a bit of what these objects are. So you might have seen Reed-Solomon code beforehand. So I'm going to define them again, just for convenience. So these are evaluation of polynomial over a given domain, over some of a given degree, over some domain of a larger size. So for us, we'll also be interested in the rate of the code, which is the measure of how much redundancy the encoding has. And you might be wondering why have I put the degree as 2 to the m, is because later on we will be working with multilinear polynomials, and this makes things much more convenient. An IOPPO proximity for Reed-Solomon codes, then, is a way to test proximity to Reed-Solomon codes. And what does that mean? Well, it will be an IOP as between a prover and a verifier, but additionally the verifier gets oracle access to some word. And the goal of the verifier is to tell whether this word is a Reed-Solomon code word or not, while still making few queries to it. So by completeness, if the function is a Reed-Solomon code word, the verifier will accept. While the soundness condition says that if f is very far in terms of Hamming distance from a Reed-Solomon code, so it differs from a polynomial encoding in many places, then the verifier will accept with small probability. And our goal, we saw before that queries translate to argument size, so we want to minimize the number of queries. The notion of soundness that we require is that of round-bound soundness, because later on we need to compile with FHMER, so our protocol needs to satisfy this as well. Okay. So I want to this is how things have been done traditionally. Now I'm going to talk a bit about how you can improve this recipe by doing something that we call constrained Ritz-Solomon code test. So what I showed you before, you basically were running this Ritz-Solomon proximity test on this quotient function. And the reason this was done is because the prover wants to show to have a polynomial and a commitment to an encoding of it, such that the polynomial evaluates to a certain point at a certain value, to a certain value at a certain point. Okay, this is really what we want to do. This is how we want to take the polynomial IOP and compile it into an IOP. And you can think of this test that is being run as the following, as a test for a constraint encoding. So in a sense, I'm taking first I'm taking the function, so my commitment, and I'm quotienting it. And you can think of this as like embedding the constraint into something that then we can check with the Ritz-Solomon proximity test. So the reason why we care about the test is because it allows us to check the constraint. So the question that we ask is like, can the proximity test instead directly enforce the constraint without having to go through this awkward quotient step? Turns out that it can, otherwise I wouldn't be here. So you can design these IOPPs for constraint codes, as I will see in this slide. So, okay, I'm going to take the Ritz-Solomon codes, and I'm going to do some trickery about them. So traditionally, Ritz-Solomon codes are about univariate polynomials. But turns out that you can actually rewrite them about multilinear polynomials. So by each multilinear polynomial query that is specific power bit vector things will give you the evaluation of a univariate polynomial with the same coefficients. So I'm just going to rewrite this, and it will give us a lot of flexibility. And now I'm going to extend these Ritz-Solomon codes to additionally have two other parameters, a constraint polynomial and a value this constraint. And this constraint code will be obtained by taking the Ritz-Solomon codes and just additionally stating the sum constraint solved. So this constraint is, I call it a sum-check constraint, because later on we will be using sum-check to check this. This is why they have this specific form. So you can check that if this constraint Ritz-Solomon code is instantiated with the zeros in the new parameters, you recover Ritz-Solomon codes, and you actually get something more. So for example, if I set the constraint polynomial to this form, you actually are able to prove directly multilinear polynomial evaluation. And we want to then test proximity to this constraint Ritz-Solomon code. Okay? So with these preliminaries, let me tell you about a result. So we build WER. So WER is a constraint Ritz-Solomon proximity test with state-of-the-art prover time, query complexity, and verifier time. So the most important thing in an IOP is the query complexity, which in WER, in typical setting parameters, that is when the security parameter is much larger than the number of variables, achieves a query complexity which is log in the number of coefficients of the polynomial. This case is a folding parameter, and setting it to be roughly log as well allows you to achieve, in fact, of security parameters, query complexity, which is optimal as far as we know for IOPPs. We further show how to get how to use this constraint Ritz-Solomon proximity test in order to take a new notion that we introduced, which are called sigma IOPs, and compile them into an IOP, similarly to how the quotient compiler was done for the Ritz-Solomon proximity test. Further, we also have implementation, we have code, we have a bunch of nice facts. So let me compare this with prior work. So WER inherits the same improvements in query complexity of stir over fry and basefold. So while both fry and basefold ended up having like a linear dependency on the number of variables in the number of queries, the stir and WER ends up having a logarithmic. So you have an exponential improvement there. Further, over stir, we improved on the verifier time. The verifier of stir ended up having a quadratic dependency on the security parameter, while WER removed this entirely. by in an appropriate parameterization, both the queries and verifier time of where are optimal for IOPPs. Where the improvement can be is in the alphabet, which is larger than what it could feasibly be. This alphabet size could be constant, so improving this is a very exciting open question, in my opinion. Just to give you now some numbers, so here I have put some graphs. There's fry, stir, and whir. So you can see that fry is the red line. Whir improves in argument size, hash complexity on fry significantly, while matching stir. And when it really shines is in the verifier time, which is much smaller than both fry and stir. I also would like to say that the prover time graph is now updated because we found out a lot of optimization in the meantime, and you look, I didn't have the funding to run the other benchmarks. So, particular to give you some numbers, especially when the coefficients are large and the rate is large as well, you get like a very sizable improvement over fry in concrete proof size. Okay. Further, whir as something achieves a new notion, which we call superfast verification, which just means that the verifier is pretty damn fast. So the whir verifier typically runs in a few hundred microseconds, while other verifiers require several milliseconds or more. So this is all while maintaining state-of-the-art prover time and argument size. So just to give you some numbers over here, the whir verifier is faster even than schemes like PST and KZG, which are schemed with a trusted setup and using heavy elliptic curve operations such as pairings. In particular, these ones, they asymptotically would beat whir. They have constant proof size, but the constants are just end up like making it slower in concrete verification. So whir also, we have an implementation. We started working on it. We felt that the practical performance of the protocol would be very nice, and it turned out that these two have spurred quite a sizable number of efforts in concrete implementation. So, for example, the initial implementation is leading to it led to a word client-side prover, a client-side prover for the Word project, which means that Word will be deployed to more than 26 million of users later this year. We've managed to also, another thing that we wanted to investigate is that we have a very efficient verifier. Currently, a lot of the verification on-chain relies on proof systems like Graph16, which have to use elliptic curve operations. So we had a thesis that Word would be competitive with these schemes, and indeed it is. You're able to actually verify a proof fully with a transparent setup, post-quantum on-chain, with very little with competitive verification with pre-quantum alternatives. All of this has made Word very popular, and Ethereum is also considering it as part of its transition to the post-quantum, something which I'm very happy about. So there's been a lot of other efforts. We have Plonky-free implementations. There's been a CUDA-based implementation with GPUs, which can prove now more than 1 million hashes a second. But the thing which I'm the most happy about this is that there's an ongoing formal verification effort of Word to make sure that the security claims that we make actually are substantiated. So, to conclude, in this talk, I haven't been able to go much into the techniques. At an high level, you can think of Word as being a clever combination of the rate improvement techniques of stir with some of the multilinear to univariate characterization of Gemini and Basefold. But at an high, the takeaway is that Word is this new IOPP for this constraint with Solomon proximity code relation with state-of-the-art query complexity and verifier complexity. Further, prover time and argument size and hash complexity of the resulting argument are also state-of-the-art. You get the fastest verification of any polynomial commitment scheme out there, including those with trusted setup. There's been rapid practical adoption, which I think I was very, very happy to see. And we also showed that this enabled high soundness compilation for the Sigma IOPs. And since I have a bit of time, I think one exciting open question is whether this new flexibility in the Sigma IOP setting would allow to do more efficient proof system by leveraging clever argumentizations. So to conclude, there's an open question. There's the, which I think is the most exciting question in this area. Where is getting very close to what are the limits for IOPPs in terms of information theoretically, what we can achieve in order of argument size of the compiled argument. So we know how to improve it by doing significantly more prover work. By making the prover work more, we're able to reduce the proof size considerably. The exciting open question is, can argument size be brought even down, even lower, at the same prover cost? So this was my talk. Thank you.
We do have time for questions.
Oh, perfect.
Ciao Giacomo, bellissimo, mi piace. Super, super cool work. I had some questions about your benchmarks on KZG and PSD.
Yes.
The numbers there seemed a little bit like 3x higher than they should be. Like, did you use state-of-the-art libraries or?
I used the ArcWork library. I used the ArcWork library. I think for PSD there wasn't a direct implementation in ArcWork, so I took the one from the MP Labs multivariate polynomial commitment repo.
Yeah,
So
we can chat offline. I feel like the numbers should be much
yes,
lower.
I can yeah, we chat about this.
And the numbers for was that under those error-correcting conjectures that are unproved, or was it under proved?
So like in this, so for that one, I think I was using the conjecture. Yes.
Conjecture.
Yes.
Okay. The most aggressive one.
Yes, the one with the up to capacity.
I see. And do you have a sense what would happen when you use something that's?
So like for the verifier size, you can imagine. Usually the conjecture moves you from like the number of queries doubles. So the majority of the verifier of WER ends up being hash verification. So you can think of it from like from a 2x worsening to like 1.f depending on what's the relative cost of field operation and hashes.
Yeah, still very good. Super impressive that it's competitive with Graph.
Thank you.
Yeah.
Any other questions? I have one question. So when you were putting up all the implementation, there was a lot of ZK there, and as Ellie said yesterday, ZK, right? What would be the additional overhead to add ZK to something like this?
That's a very exciting question, I think. Like a very interesting. So we know how to do it with the, let's call it almost generic techniques, in which involve basically the prover committing to an additional polynomial of the same degree as the one that you're doing. So this basically doubles the data that you have to commit for the prover. For the verifier, the slowdown is not much. You don't really feel it on the verifier side. So you can think of depending on the case, like a 1.5x prover slowdown, let's say. I think it's very exciting to see whether like this seems too much randomness. It doesn't seem like masking this much would be like necessary. So I think the exciting question as well is to try to see whether this can be brought down.
Right. One of the things that I was thinking was we were able to constrain and get rid of the division and put everything in one place. Maybe that ZK could, instead of adding another polynomial, maybe there could be a way.
I think so. I think yes. I'm definitely looking into this.
Great. Thank you. Let's
Thank
do
you.
the speaker again.
Thank you.
We have one more talk. So the last talk of the session is Query Reusable Proof Systems by Yuval Ishai, Eyal Kushilevitz, Varun Narayanan, Rafael Ostrowski, and Akash Shah. And Akash will be giving the talk. Thank you.
Hi, thank you for the introduction. So in order to motivate our work, let us consider the notion of non-interactive zero-knowledge proof, and let us see how, with designated verifier, how they can be constructed using watch list. So here, in the setup gives a set of random mask of length n to the prover, and the verifier receives a subset of this mask, and this subset is basically the watch list. This corresponds to the list of bits of the proof that the verifier can see. Now, given the input x and witness w, prover computes a proof pi and sends it to the verifier. Verifier given, and this proof is of course masked with the CRS, and verifier given the watch list, it can unmask the bits and read the proof bits corresponding to the watch list. And it can accept or reject the proof. Now, the proof system, PV, has the following properties. That is, it should satisfy the notion of correctness. That is, if the relation R on input X and W outputs accept, then the verifier should accept. And the soundness requirement is that if X does not belong to the language, then verifier should reject with overwhelming probability. Zero knowledge requirement is that there exists a simulator that, given the input X, should be able to simulate the bits of the watch list that is read by the verifier. Now, as the title of our paper suggests, we are interested to ask this question, that is, can we reuse the watch list across multiple input instances? So for this, we tweak the base protocol that we had. That is, now instead of considering each Ri to be a masking vector, we consider each Ri to be a key to a symmetric encryption. Now the prover, given the input X and witness W, it's going to generate a proof pi, and it's going to encrypt each bit pi I using the encryption key Ri and send it to the verifier. Now, this system is going to be zero knowledge because the verifier only knows the keys corresponding to the watch list. So all the other proofs, all the other bits of the proof are encrypted, and the zero knowledge is guaranteed due to the security of symmetric encryption scheme. So the question that we want to ask is whether this proof system is sound. Well, it is sound if the prover does not learn verifier's decisions. However, if verifier's decisions are learned by the prover, then it can mount a simple selective failure attack. So the failure attack works in this manner. What the prover can do is that it can take an input X and find the corresponding proof pi. Then it will compute a proof pi I, where pi I is computed by flipping the ith bit of the proof pi. And then it sends this list X comma pi I to the verifier, and verifier will then accept or reject these proofs. And from this rejections, prover will be able to determine the proof pi I that the verifier had rejected, and from this it can construct the entire watch list. And this attack basically works for all the watch list based constructions in literature. So of course, as we can observe that there are simple ways in which we can circumvent this attack. That is, we can have each bit of the proof to be replicated, and then verifier can do majority voting and so on. But then there would be slightly sophisticated attack that could still work. And indeed, in our paper, we'll show that we can construct robust ZK PCPs for a bounded with some bound. And we need to ask this question that can this attack be generalized and attack all kinds of ZK PCPs? So the question is this attack inherent? So now we'll abstract the proof system and the underlying watch list protocol as a ZK PCP. So here, the prover computes a proof pi and gives oracle access to the verifier. Verifier is going to sample a set S and probe the bits of the proof at these locations and decide to accept or reject the proof. Now, the these properties of honest verifier ZK PCP is exactly as discussed for the underlying PV proof system in the watch list protocol. So we'll skip that. Here we formally define the notion of query reusability for ZK PCPs. So here, a query reusing verifier will sample a fixed set S once and for all, and then the prover will run for polynomially many rounds. It will send an input X along with a proof pi, and it will learn verifier's decision on this input proof pair. Now, after polynomially many rounds of interaction, prover will come up with an X star that does not belong to the language and a proof pi star. And if verifier accepts, then the prover wins the game. So now the notion of query reusable ZK PCPs is interesting because then we can construct designated verifier NIZICs from only one-way functions. Standard NIZIC protocols in literature require structured assumptions like factoring, discrete log, LPN, and so on, and some constructions are based on random oracles. And this question is practically interesting as well because we can construct concretely efficient designated verifier NIZICs, especially in the setting where we are OK with non-negligible soundness error. This setting is interesting when the prover suffers a loss of reputation, or it can have legal consequences if it's found cheating. If we make use of this compiler, then we would be able to avoid soundness amplification and hashing cost that is inherent in Fiat-Shamir heuristic. So now let us see what are the previously known results. So here, as discussed, for query reusable honest verifier ZK-PCPs, it is easy to achieve if the verifier's decision is private. However, there was a negative result in Crypto 19 paper by Chase et al., which said that it is impossible to achieve even against computationally bounded prover with computational ZK. However, they assume a strong notion of simulatability. And I would like to stress that that result does not hold for the standard notion of honest verifier ZK-PCPs. So in this work, we show that statistical honest verifiable ZK-PCPs are not reusable. However, we also show that bounded reusability is still a possibility, which we elaborate on in the next slide. And we also show that if we restrict either the prover or verifier to be computationally bounded, then we can get rid of the impossibility. This shows that the limitation of simulatability in the previous work was in fact necessary, because if you lift that limitation, then you can get a computationally bounded ZK-PCP. So to elaborate more on our results, let me first formally define the notion of R-epoch bounded query reusability. So here, the query reusing verifier samples a set S once and for all, and the prover will then engage in R many epochs of interactions with the verifier. And in each epoch, the prover will send polynomially many instances of input proof pairs, and it will learn the verifier's decision on this input proof pairs. And at the end of R epochs, if the prover is able to break the soundness property, then it wins the R epoch bounded query reusability game. So now, with respect to this notion, we have a negative result. That is, we show that any ZK-PCP with query complexity Q is only query reusable in at most root Q epochs. And here, like O tilde and omega tilde suppresses the polylog terms. And we have the positive result, that is, we show that there exists a statistical ZK-PCP with query complexity Q, which is query reusable for cube-root Q epochs. And assuming LWE, we show that there exists a fully query reusable computational ZK-PCP proof or statistical ZK-PCP argument. And we also have this negative result for other class of PCPs, and the same applies for our positive results for statistical ZK-PCPs. So now let me first give a higher level overview of our statistical ZK-PCP positive result. So as a warm-up, we start with the zero testing. So here, we want to determine whether the input vector X is a zero vector. So the test will probe few locations of the input, and the test is correct if it always accepts a string, a zero vector, and it is sound if it rejects any string with Hamming distance greater than n by 2 with overwhelming probability. So now let us consider the simple test, which what it does is that it's going to sample a set S of size log square n, and it is going to read the bits of the input vector in this set, and if any of this bits is 1, it is going to reject the input. So now it's clear that this simple test is indeed valid. So we have this question: can this test be assured to be R-epoch? Does it satisfy the notion of R-epoch bounded query reusability? Well, it doesn't, because the selective attack that we showed earlier works for this problem as well, and it is as follows. So you have an input vector which is all. You start with a string that is all zeros, and you flip one bit at a time, and this way you will be able to recover all the bits for which the tester rejects the input. So then let us first discuss a tester that works for one epoch, then we'll extend it to a tester that works for R many epochs. So now what this simple tester does, this somewhat simple tester does is that it's going to sample two sets, S1 and S2, and it's going to accept X only if all the bits in S1 are 0, and at most 1/4 fraction of the bits in S2 are 1. So now in this test, you can verify that S1 actually acts as an attractor. This is because if the test fails, then with overwhelming probability, the test failed because the test failed on S1. This is because suppose you have you have a setting, you have the case in which S2 failed and S1 passed. This can happen with negligible probability because what you are trying to say is that in the set S1, you found all zeros, and in the set S2, you found more than 1/4 fractions of ones. So by Chernoff bound, we show that this happens only with negligible probability. So in some sense, the tester's decision can be simulatable by knowing only the set S1. So as such, the set S2 after one epoch is not known to the adversary, and adversary as a result cannot bound an attack. So now this idea can be extended to our many epochs. So the idea is that instead of having two sets, now we have S1 to SR+1 sets. Now here too, S1 is the most unforgiving test because it rejects if any single bit in S1 is 1. S2 is slightly better, but still it's more forgiving in the sense that it would still reject if 1/4 R many bits are 1. More than 1/4 R bits are 1. And we can argue this until the set SR+1, which is the most tolerant because it will allow for 1/4 fractions of bits to be 1. So extending this argument that we had earlier, we can show that at the end of epoch K, all the decisions of the tester can be simulated by knowing only the query sets S1 to Sk. This is again due to the reason that if the test failed, then with overwhelming probability in epoch K, the test would fail because the test failed on sets S1 to Sk. So now we can extend this, we can reduce the notion of reduce the proof for R epoch query reusability to R epoch query reusability of zero testing. So this reduction works in this manner. So here you have R+1 groups of sets, and each R+1 groups of sets comprises of R square log square n groups of query sets. And the verifier's decision on these groups of set can be connected to probing the bit in the zero vector testing. So with this relation, you can reduce the R epoch query reusability of PCPs to the R epoch query reusability of zero tester. The solution for ZK PCPs is exactly for PCPs, except that we need to take care of zero knowledge. So instead of just using one proofs, we are going to issue independent proofs so that verifier does not learn sufficiently many bits in order to learn the underlying witness. So now we come to our negative result. So I'll give you a high-level overview in which we show that we can construct an adversary that learns the entire query set in root Q epochs. So as a warm-up example, let us consider an attack that helps you to recover one bit, one coordinate from this query set. So in this hybrid attack, what you do is that you pick up an X in the language for which the verifier rejects an all-zero string as proof with high probability. So what you will do is that you will progressively replace each coordinate of the proof with 0, and then you will output the coordinate for which the verifier's decision changes from accept to reject. Now, this attack cannot be repeated to learn randomly many coordinates in S. This is because you have no way to guarantee that in each execution of this hybrid attack, you'll be learning a new query set. There is a possibility that you'll be relearning the same query coordinate again and again. So now let us discuss the blueprint of a stronger attack. So in this attack, we define the notion of residual PCP, which is the PCP that is constrained on the verifier's output or on the verifier's output that are learned by the prover over time. So then once we construct this residual PCP, which has high soundness error, then you would be able to learn input, proof, which the verifier accepts such that the input X does not belong to the language. Or else, you can use this hybrid attack, which I mentioned in the previous slide, to learn an unknown coordinate in S. And after repeating this logic multiple times, you keep updating the view and keep shrinking the query set from which the view of the verifier could have been sampled and in the residual PCPs. So more formally, the prover at a point learns the the output bit B for input X and proof pi from the verifier. And then this is the prover's view. Now we are going to constrain the prover's query set to be picked from the query set, which is consistent with the prover's view. So now we have the following conditions. First, in each logical step, we check if there exists an X that does not belong to the language and there exists a purported proof pi such that the verifier accepts with probability greater than 1/3. So if this query reusing verifier accepts, then the attack has already happened and we have succeeded. Otherwise, we would be able to shrink the query set by a factor of 1/3. And in the other case, we'll use the hybrid attack that I mentioned in the previous slide to learn the new query set, a new coordinate. But if we would not be able to learn a new coordinate, then we should be able to shrink the query set again by a factor of 1/3. Now, there is only one thing that is left to discuss. That is, what if both 1 and 2 cases do not happen? Well, if that does not happen, then if that happens, then it contradicts statistical ZK, unless co-NP is contained in NP/poly, which refutes a complexity conjecture, and the argument is similar to what was used by Fortnow in '87. And to mention briefly, touch upon our final result, that is construction of fully query reusable ZK-PCPs in the computational setting. So what we do is that we obtain fully query reusable ZK-PCP by combining NIZK proof arguments in the CRS model along with non-interactive secure computation in the OT hybrid with statistical semi-honest security. And then we make use of Waters' NIZK argument using LWE. So combining these two results, we get so basically, by using Waters and NIZK proof in our compiler, we would be able to obtain a fully query reusable computational ZK-PCP proof or a statistical ZK-PCP argument. Yes, thank you. Any questions?
We have time for one, maybe two questions. Okay, so let's thank the speaker again and all the speakers of the session.